Good afternoon.
Good afternoon, ma'am.
Good afternoon.
Good afternoon, ma. So we have seen in the last class bilinear transformations. So we did the transformations of normal curves and other things using the standard transformations. And then we have seen suppose you have to draw all the transformations in a 4D plane, it's tedious. So we saw the transformation from one plane to the other plane. Okay. So this was about the first and the second module. What did we see in the first module? In the first module, we have seen analytic functions. Okay, analytic functions and other things. What are the other things? Applications of the analytic functions also we have seen. Okay. Now, next one, we are going to move on to the third module. Okay, we are going to move on to the third module where we are going to see the complex functions in series expansions. Okay, when we are going to see the complex functions. Actually, no, the complex integral we have to solve. So the integrations we'll see in the fourth module. So to solve some integrals, suppose we are not able to solve it, we are going to use any of the series. Okay, the power series with using the power series expansion, we'll expand it. So when we are using power series, so let me tell you first of all what is a power series. Okay, now we are going to talk about module 3. Okay, module 3. So we are going to talk about power series first. So when we are going to talk about the power series, what is a power series? Is a series of the form n is equals to 0 to infinity an into z minus a whole power n. So this is a power series in z minus a. Once you expand this, how it will be? It will be a naught into z minus, sorry, a naught plus it will be a1 into z minus a plus a2 into z minus a the whole square and so on. So this will be the power series expansion. So what is this a? A is called the center of the series. A is called the center of the series. What is this z? Z is your complex number. Z is your complex number. Okay. Z is your complex number. A is the center of the series and this a naught, a1, a2, etc. are constants. The coefficients of what, ma?
Ma'am, you have written a n also there. Sigma n equals to 0 from infinity a n z minus a to the whole power n.
Yeah.
If you don't mind, can you please explain it once more?
I was only explaining this only, no dear. I don't understand. Every day you have some or the other problem and you keep on interrupting it. Is it problem only with you or with everyone else? I just want to know today.
Network issues there are like a lot. So
every day you cannot have the network issue, dear. One day is fine. In that case, you have to change
really
your network.
That's why.
Correctly, I'm saying if you have if you are having a everyday network issue, you should change your network. That's it I can say. I am not coming on exactly at 3 dot and asking you people to sit here and do. I'm giving you time. Already I'm coming little 5 minutes, 3 to 4 minutes late only I'm coming. I'm not coming here at 2:55 and I'm asking, I'm starting the class. I'm giving you time for you all to get settled. Is anyone else has any other problem? Because I have completed 2 modules. If you have any problems, if you say now itself it is be better. After CAT or after term, and if you say you have so many problems, you had these all problems, it's of no use. You can just tell me, you can feel free and tell me anything you want me to change. I can change even now. I have no objection. Anyone else has any other problems? Please reply, ma.
No, ma'am. No, ma'am.
So you all understood what I was telling today?
Yes, ma'am. Yes.
Yes, ma'am.
Okay, fine. So I didn't even start anything. Actually, I was trying to say there is a powerful expansion called a power series expansion, where when we have to integrate any complex function, we can even use the power series and we can integrate the complex function. So mainly this power series was brought into the concept to solve the integral equations, So a general power series will be of the form summation n is equals to 0 to infinity a n z minus a whole power n. So suppose you give values for n, what will happen? You'll get a naught a1 z minus a into z minus a and the whole square. What is this a? A is called your center of the series. A is called your center of the series. A naught, a1, a2, etc. are your constants. They are called even the coefficients of z minus a. They are also a1, a2, etc. are also coefficients of z minus a and so on. Okay. So a naught, a2, a3, etc. are also constants. So whenever we are talking about the power series, from the power series, we have two other series which we are going to see in the, one is Taylor series. Okay. One is Taylor series and other one is Lorentz series. I hope you have studied Taylor series already. Okay. Yes or no? Have you all ever come across the Taylor series?
Yes, ma'am.
Yes,
Yeah. Yeah,
Yes,
whatever the Taylor series you have studied in your real calculus, okay, whatever you have studied your Taylor series in the real calculus is the same old thing we are going to see here, but here we are going to see it for the complex numbers. But here we are going to use it only for the complex numbers. There you would have seen for the real numbers, same type of application we are going to see here using the complex numbers. So why are we using all this power series in the complex expansion? It is only to solve the integral equations or real integral equations. Whenever you have to evaluate it, we are not able to evaluate in a normal form. We try to convert in some series and we try to evaluate it. That is the idea of the Taylor series and the Lorentz series. Okay, so if you want, you can take down the definition of the power series. You can just take down a series of the form. Summation n is equals to 0 to infinity. You can see there. Summation n is equals to 0 to infinity a n z minus a whole power n. A series of the form summation n is equals to 0 to infinity a n into z minus a whole power n is called power series. In powers of z minus a. In powers of z minus a, where z is a complex variable. Where z is a complex variable. Z is a complex variable and the constants a naught, a1, etc. are called coefficients. A naught, a1, etc. are called coefficients and the constant a is called center of the series. And the constant a is called the center of the series. Okay. Then you can just directly take down the Lorentz series expansion. Sorry, Taylor series expansion. Take down if f of z is analytic in a circle C. If f of z is analytic in a circle C, okay, in a circle C with the center at A, and the radius R0, with the center at A and radius R0, then at each point inside C, the function f of z can be represented as, so f of z will be equal to, you can just take down f of a plus f dash of a by 1 factorial into z minus a plus f double dash of a by 2 factorial into z minus a the whole square plus etc. plus f power n of a by n factorial into z minus a whole power n plus etc. What is A? A is the center of that given circle. Okay, and radius is R0. Okay, radius is R0. In that case, any point you take inside that circle can be represented in the form of a Taylor series expansion. So how the Taylor series is f of a plus f dash of a by 1 factorial into z minus a, f double dash of a by 2 factorial into z minus a the whole square, and so on. This it is again a representation of a power series. Yes or no? You have some powers, z minus a the whole square, z minus a whole power n. Okay, so that's why from the power series only we get the Taylor series as well as the Lorentz series. Okay, and what is this where this f power n, where this f power n denotes nth derivative, denotes nth derivative, where this f power n denotes nth derivative. Then take down Maclaurin series. Maclaurin's Maclaurin series. Do you remember Maclaurin series? You have studied even this.
No, ma'am.
No, ma'am.
Real a
Yes, ma'am,
Maclaurin.
the radius is at the origin.
What is Maclaurin series, ma?
Radius is at the origin.
Very good. Radius is at the origin. Maclaurin's, I think I have spelled it wrongly. Yeah. Maclaurin series. Okay. When A is equals to 0, that is the center is at the origin. Write down. When A is equals to 0, in the bracket you can write down center at the origin. So what will happen to your series? Your center is at the origin. So wherever A you have, you're going to replace it by 0. In that case, your f of z will be equal to f of A plus f dash of A by 1 factorial into Z plus f double dash of A divided by 2 factorial into Z square and so on. The nth term will be f power n of A by n factorial into Z power n and so on. And so on. Same thing is whole good. Again, the circle with the center at origin, that only you will speak. Okay, center at the origin, and the radius is going to be r0, and any point can be represented in the circle using the Taylor series expansion is known as a Maclaurin series if the center is at the origin. Then when I'll give off the definition even for the Lorentz series. When you see this Taylor series, you can see all are positive powers, the 1, 2, 3, and so on. There is nothing like z power a minus 1, z power a, z minus a whole power minus 1, z minus a whole power minus 2 is not there. That is 1 by z minus a, 1 by z minus a the whole square, 1 by z minus a the whole cube is not there. So to track even that, the Lorentz series expansion was used. Okay, so the difference between the Taylor series and the Lorentz series is the Taylor series will have only positive powers of z, whereas the Lorentz series will have the positive powers as well as the negative powers of z. So it consists of two parts. One is positive expansion, other one is the negative expansions of z. Okay, you can just take down. So since we have two series here, that is negative powers as well as the positive powers, how the series is represented is the series is represented in a concentric circles. You know what is a concentric circle, right? How will be the concentric central?
Having the same centers.
With the same centers. Yeah. So you'll have a concentric circles. So using the concentric circles, we are representing the Lorentz series. Okay, you can just take down let C1 and C2, let C1 and C2 be two concentric circle. Be two concentric circle, that is mod z minus a equal to C1 and mod z minus a equal to C2. Sorry, why did I write C1? C1 and C2 are circles. Radius I should write, right? You can take as R1 and R2, ma. R1 and R2. So Z minus A is equals to R1 and Z minus A is equals to R2. And R2 is less than R2 is less than R1. R2 is less than R1. So this will be your R2. This will be your R1. Let f of z be analytic. Let f of z, the function, we are talking about the analytic functions, right? So f of z be analytic on C1 and C2, on C1 and C2, and in the annular region. This is your annular region. Okay, so f of z is analytic on the curves C1 and C2 and in the annular region, capital R and in the annular region capital R between them. And in the annular region capital R between them. Then for any point Z, then for any point Z in R, then for any point Z in R, your f of z, okay, your f of z, you can represent it as summation n is equals to 0 to infinity an into z minus a whole power n plus summation n is equals to 1 to infinity bn divided by z minus a whole power n, bn divided by z minus a whole power n, where, okay, just take down, f of z is equals to summation n is equals to 0 to infinity an into z minus a whole power n, summation n is equals to 1 to infinity bn into z minus a whole power n. See, if you remove of this, suppose you remove of this term, what it will be, ma? What is that?
Taylor series.
This is a power series expansion. So basically Lorentz series is also an is from the power series. Only the thing is you have here positive powers, here you have negative powers. Okay, so you have positive powers of z and here you have negative powers of z. That is the only thing you have in this Lorentz series. Okay, now you should know the constants. What are these constants? an and bn. So write down where an is equals to, where an is equals to 1 by 2 pi I integral over c, 1 by 2 pi I integral over c f of z, z minus a whole power n plus 1 into dz, where an is equals to 1 by 2 pi I integral over c f of z divided by z minus a whole power n into dz. So there are two curves, so you can take it as c1 here. Similarly, your bn will be equal to 1 by 2 pi I integral over c2, okay, integral over c2 f of z divided by z minus a divided by z 1 minus n whole thing into dz, 1 minus n whole thing into dz. One minus n whole thing into dz. Okay. Now you should know when I'm talking about the Lorentz series. So I told you you have a series expansion. So in the series expansion, there are positive powers and the and the negative powers of z. So what is this positive power and the negative powers of z is called, that you should know. Okay. So sorry. So this is your regular part. This is called your principal part. Okay, so that is called your regular part. The other thing is called as principal part. So always the Lorentz series is comprising of two parts. One is the regular part, other one is the principal part. So a regular part is as usual, you have the positive powers of z. The principal part will have even the negative powers of z. Is anyone is having any doubts in the definitions of the Lorentz and the Taylor series?
Excuse me, ma'am.
Tell me, ma.
Ma'am, why the functions needed to be analytic for the expansions to be valid?
What, dear?
Why must the functions be analytic for the expansions to be valid?
This is only valid for the analytic functions. This Lorentz series and the Taylor series in the complex, we are only considering only for the analytic functions. What is the advantage of the analytic function? Go back to the definition of the analytic function. What is there in the analytic function?
They're differentiable.
It is differentiable. That's it. The functions is differentiable. What does ultimately the differentiable means?
Different derivative exists.
Derivative exists means, that means what?
It's continuous.
Continuous
At all
also.
regions.
Continuous. And one more thing you can say. What is that? Only continuous. The function value exists, right?
Okay.
The mainly
Yes,
is, if it is differentiable means functions value. That's why we talk about here only the analytic functions. Is it clear?
Yes, ma'am.
Okay. So we'll do some problems. Before that, I just wanted to confirm one thing. Yes, I wrote it correctly or not, I had a doubt. Bn z minus a whole power minus n. Yeah, n I wrote it as denominator. Fine. So this is called your principal part and that is called your this one. So actually, no, what is that actually? What we are doing is we are trying to find this constants actually in the series expansion. So here we have integrations. You can see, I told you, no, it is used to solve only the integral equations. So we have integrations to solve it. So complex integration, we will see it later. So we are seeing the power series first. So I will do it using the series method first. I'll do it using the series method first. Is it clear? Okay, you can just take down first problem. Before going into the problem, I just wanted to give you a few formulas also. You can just take down. So you know what are the formulas for 1 minus x whole power minus 1, 1 minus x whole power minus 2, 2. Do you know? Some important results you should know. 1 minus z whole power minus 1. Can anyone tell me what will be the expansion series for this?
1 plus z square plus z cube.
1 plus z square plus cube. This series is valid only for what region? When
It is not equal to
mod z is less than 1. When mod z is less than 1. Similarly, 1 plus z whole power minus 1. What is this? 1
alternate
minus z.
plus.
Yeah, alternate minus plus. Very good. Alternate minus plus. And this is also valid only if mod z is less than 1. Other than that, you remember what is e power z expansion? E power x expansion, you know, no? Same thing will be in terms of z.
When it
1
comes to
plus.
factorial, right?
Huh?
It comes to factorial, right?
Yes, yes. 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial and so on. This series is valid only when mod z is less than infinity. And similarly, e power minus z, you will have alternate plus and minus sign. That's all. 1 minus z by 1 factorial. All this I'm telling you before itself because we are going to use all these things. And so on. 1 minus z by 1 factorial plus z square by 2 factorial minus z cube by 3 factorial and so on. Even this series is valid when mod z is minus 1. Anyone remembers the expansion for sin z? Expansion for sin z?
Z minus Z cube by 3 factor.
Z minus z cube by 3 factorial plus z power 5 by 5 factorial minus etc. Even this series is valid when mod z is less than this. Cos z expansion? 1 minus z square by 2 factorial plus z power 4 by 4 factorial minus etc. Again, this is mod z less than infinity. Sin hz might be you don't know. It is very simple. Here you have alternate plus and minus and everything will be positive. That's all. Nothing. Z plus same cos sin z expansion, but all are positive. And so on. Similarly, cos hz will be 1 plus z square by 2 factorial. This is z. This is 2 ma. Don't get confused. 2 factorial plus z power 4 by 4 factorial plus etc. Everything is mod z less than infinity. Mod z less than infinity. Do anyone remembers the expansion for 1 minus z whole power minus 2? One minus x whole power minus 2.
1 plus 2z.
1 plus 2z plus
3z square.
3z square plus 4z cube and so on. You can make a note of all these formulas. Because first I'm going to talk only using the series expansion. I'm not going to talk using the integrations because I have to teach you complex integration and then only we can do the expansion. So first we are going to talk only about the series expansion. So in the series expansion, we are going to use all these results. Have you all completed? If you have completed, you tell me. I hope you all are taking notes. One fine day, I'll ask you to scan your notes and send me to add for the DA. Shall I do it? And you are writing quiz. You can write quiz on Tuesday. Tuesday we have 6 to 7 class, right?
Yes, ma'am.
Yes, ma'am.
We can avoid that class. So we can do quiz on Tuesday because already I am in safe position for the CAT 1. So CAT 1, you may, I'm still, I don't know, they have not yet confirmed it. Module 1 and Module 2 is there for sure. Module 3 is there or not, I'm not sure. I will confirm it by today, next class, that is Friday's class.
Ma'am, what will be the final syllabus portion for the quiz?
Syllabus for the quizzes, Module 1 and Module 2 on the date itself, I said, no, ma.
Okay, ma'am. No, ma'am, there were some speculations that there will be half of the module 3 also, or something like that.
No, that is only for the CAT, I said, not for the quiz.
Okay, ma'am. Ma'am, how much will be the time for the quiz given?
10 minutes, 10 questions.
Ma'am, can it be 15?
That I'll see after setting up the question paper.
Okay, ma'am.
So you're writing the quiz, it is fixed for Tuesday evening. So the one who wants to take vaccine also can go and take vaccine on Monday. Correct only, Rama?
Ma'am, it will be in class hours.
Yes, it will be in the class hour. For 15 minutes and there will be no class after that. You are going to come, give the quiz and go. So one who is going to give the quiz will get the attendance for that class. Okay. You can just take down, obtain Taylor series expansion, obtain Taylor series to represent the function. Obtain Taylor series to represent the function f of z is equals to z square minus 1. F of z is equals to z square minus 1 divided by z plus 2 into z plus 3 divided by z plus 2 into z plus 3 in the region mod z less than 2. In the region mod z less than 2. So listen, I told you now I'm going to use series, expansion, and I'm going to expand this function. So normally you can find f of z, f dash of z, f double dash of z at the point whatever it is given, and we can expand it. That is one way of doing the problem. The other way is, what I'm going to do is, first of all, I'm going to split this in terms of partial fractions. Do you all remember what is a partial fraction? You would have studied in AOD, right? Yeah. So what is the basic rules of the partial fraction, ma?
Ma'am, denominator power should exceed the numerator.
Denominator is splitted.
Denominator power should be
Exceeding.
greater than
the numerator power.
If not, otherwise what you should do?
We have
Can you
to
please repeat the question you just
in the
asked?
numerator it'll
divide
be
it
1
and-
or less.
It should be like that, right? Whether this is a valid, can we directly use partial fraction for this series?
No, ma'am.
No. So what we'll do is, we'll
Ma'am,
first
Z
divide
one,
this.
Z minus 1.
We'll first divide this series. So we have z square minus 1. When you multiply this, what you will get? Z square plus 5z plus 6. Yes or no? What you will get? Z square plus 5z plus 6. Can anyone divide and tell me the answer? We'll just give 2 minutes time. Can anyone divide this and tell me the answer? You all know to divide or not?
Yes, ma'am.
So those who don't know, Just concentrate. So I have z square minus 1. I'm just writing it far apart. That's it. So you have z square here. Here also z square. So you can use 1. So when you multiply this by 1, z square plus 5z plus 6. Okay, subtract this. So this and this will be getting cancelled. You will get minus 5z minus 7. How can you rewrite this? How can you rewrite this? This f of z is equals to, you have z square minus 1 divided by z plus 2 into z plus 3. How can you rewrite it using this division? You can write it as 1 plus minus 5z minus 7. See, 1 plus minus 5z minus 7 divided by this. Divided by z square plus 5z plus 6. Is it clear? Now I can write this as 1 plus this term. Okay, I'll rewrite it here itself. 1 plus minus 5z minus 7. Denominator you can write it as z plus 2 into z plus 3 itself. Z plus 2 into z plus 3 itself. Now what I'll do is I'll take this part alone. I'll take this part alone. Okay. So now minus 5z. If you want, you can take with the minus sign. If you don't want, you can leave the minus sign also outside and you can take it. However you want, you can do. I have the answer for this, so I'll just do it with like that. So you can split it as a by z plus 2 plus b by z plus 3 using partial fractions. Okay, using partial fraction, I'm splitting it as a by z plus 2 plus b by z plus 3. Now I'll try to find the values of a and b, constants a and b. So minus 5z minus 7 will be equal to a into z plus 3 plus b into z plus 2. To find the constants, put
3a plus 2b is equals to minus 7.
z is equals to minus 3. If you put, what will happen? You will get plus 15 minus 21, right? Sorry, minus 7. Plus 15 minus 7. On the right hand side, you have minus 3. So a will become 0. So b will become 1. What's the value of b, ma? What's the value of b? What is 15 minus 7? You're getting b equal to 8.
I didn't understand, ma'am. Why did you put z equals to 3, ma'am?
What is
You
our
can
aim?
just also find the value. Oh, okay. Got it.
However you want, you can do it. Either you can compare the z square term, compare the z term, compare the constant term. By somehow you have to find the value. Put z equal to direct
Got it.
value 0, 3, anything you can do. Those are the partial fractions, right? So I have given minus 3. So I got it this as z is equals what I got? B is what, ma?
B is minus 3, ma'am. Minus 8.
Oh, minus 3. Oh, minus 1, minus b. This is correct. So minus 8. Okay, minus 3 and 2, right? Okay. So b is equals to minus 8. So this implies b is equals to minus 8. This is over. Then put z is equals to minus 2. When you put z is equals to minus 2, what will happen? You will get plus 10 minus 7. Plus 10 minus 7. And the right hand side, you are putting minus 2, right? So a. What's the
A
value
is
of
equals
a?
to 3.
A is equals to 3. Now, what is your partial fraction you had? You had minus 5z minus 7 divided by z plus 2 into z plus 3 we had. So this is equals to, your a value is 3 by z plus 2. Your b value is minus 8 by z plus 3. Okay, a value is 3 by z plus 2. B value is minus 8 by z plus 3. Now you have got this. This you can just take it as some 1, sorry, some 2, it's equation number 2. This you can substitute in this one. So substitute 2 in 1. Okay, so substitute 2 in 1. So substituting 2 in 1. What is your 1? Your 1 is only your f of z. How are you writing f of z? 1 minus of, sorry, 1 plus
8
of.
upon z plus 3. Minus of 8 upon z plus 3.
So you get 3 by z plus 2 minus 8 by z plus 3. Is it clear? Anyone has any doubts still here? minus 3 1 plus 3 by z plus 2 minus 8 by z plus 3. Okay, now what is my aim? My aim is to expand using the Taylor series expansion. What is given, ma? It is given in the problem mod z is less than 2. Mod z is less than 2. So whenever you have mod z less than, mod z less than 2, I can write mod z by 2 is less than 1. Mod of z by 2 will also be less than 1. Okay, can anyone tell me what will be mod of z by 3? Just give some value for the z. Take the value of mod z as less than 2. And what will be mod z by 3? Can anyone comment on it?
2 by 3.
No, my question is whether it will be greater than 1 or less than 1. That's it. Simple.
Less than 1.
It is lesser than
1. 1, ma'am.
1. When this itself, when you divide it by 2, you are getting lesser than 1. You are dividing by more higher number, surely it will be less only. So mod of z by 3 is also less than 1. Why did I do this? Is because this is your given region. This is your given region. So your series expansion should be valid in this region. Your series expansion should be valid in this region. Then only your expansion is correct. So therefore, this you can write it as 1 plus. Okay, this series you can expand in powers of z by 2. This series you can expand in powers of z by 3. Okay, so the first series you can expand in powers of z by 2. The second series you can expand in powers of z by 3. So what you can do is 3 by, to expand in powers of z by 2, what you should take out? You can take 2 outside. Once you take 2 outside, you can write it as 1 plus z by 2. Yes or no? You can write it as 1 plus z by 2 minus 8 into, can take 3 outside. You can write it as 1 plus z by 3. Okay, now this you can write it as 1 plus 3 by 2 into, take this to the numerator. It is 1 plus z by 2 whole power minus 1 minus 8 by 3 into 1 plus z by 3 into whole power minus 1. Now expand this. You know the expansion for 1 plus x whole power minus 1, 1 plus x whole power minus 1 when the series is mod z less than 1. So using that, you can write this as 1 plus 3 by 2 into, when you expand this, alternate plus and minus sign, right? So 1 minus z by 2 plus z by 2 the whole square minus z by 2 the whole cube plus so on. The other term will be minus 8 by 3. Okay, minus 8 by 3 into 1 minus z by 3, z by 3 plus z by 3 the whole square minus z by 3 the whole cube plus so on. Okay, you can just leave it like this, or you can actually, you can, if you want, you can write it in terms of series also. So you can write this as 1 plus z by 2 summation minus 1 whole power n, because I have alternate plus and minus sign. So minus 1 whole power n. I can write this as z by 2 whole power n. Now what is your n? N will be equal to 0 or 1. It will start from 0, right? When you put 0 only, you'll get back this 1. Okay, when will be from 0 to infinity. Similarly, the other term we will have 8 by 3. You can take it outside. You can even write it as n is equals to 0 to infinity minus 1 whole power n z by 3 whole power n. You can even take this, if you want, you can leave it like this, or you can, if you want, you can take this 2 inside. You can rewrite it as 1 plus 3 into, so summation n is equals to 0 to infinity is common, minus 1 whole power n is common. You can write this as 3 into z power n. Okay, wait, I can even take z power n outside. Z power n outside, I can rewrite this series as 3 by 2 power n plus 1. Okay, 3 by 2 power n plus 1 minus, see, minus 1 I have taken common, z power n I have taken common, and what else I have taken? That's all. So I can write this as 8 by 3 power n plus 1. 8 by 3 power n plus 1. Is it clear? Anyone has any doubts in this expansion?
No, ma'am.
No, ma'am.
Simple expansion. Only the thing is you should take care of this step. Because if you don't consider the given region, your expansion will not be valid in that region. Okay, so you should always take out if the given region, if you're doing with the series expansion, you should take care of the given region. So whatever the given region, from the given region only you should expand it. Otherwise your series will not be valid. Okay. Just take down. We'll wind up the class here. Other problems we'll see in the next class. Anyone has any other doubts?
Ma'am, for every region, first of all, we have to define that region, whether it is possible or not, and then we have to continue, right?
Any given region, your expansion should be valid in that region. That you have to check. You can even expand in powers of 2 by z, and this can be in the powers of z by 3. Alternatively, it can come. Anything it can come. You should check whether your expansion is valid in that region. Whatever the given region, your expansion is valid or not. Whether it is convergent or not. What do you mean by less than 1 here? Okay, that you have to take care.